DDIA by Martin Kleppman in Chapter 3, Storage and Retrieval. We're going to talk about database internals, key value stores, and analytical stores. I like this quote. It says, if you keep things tidily and ordered, you're just too lazy to go searching. I think this reflects the upfront organization versus search performance trade-off. And we do want to optimize for search because it's not just about you, right? It's about your team and your analysts. If your teammate runs into a production issue, they're going to want to troubleshoot quickly. Your analysts need to have good analytic experiences. So it's not just a matter, you can joke that programmers are lazy, but it's also a matter of minimizing the effort required for search is actually a really great criteria. Martin says, it's Martin, right? Yeah, Martin says that at a minimum, databases need to create and read records, which is true, but deletion is really, really important. You know, we care about not using all the space because we don't want to pay for it. So deletion comes as being pretty essential pretty quickly, and updating as well. So in theory, create and read is all you need, but practically everything needs to create, read, update, and delete. And here we start getting into analytical databases and column-oriented storage. So this is great, but we're going to start with just your basic create and read, and here we do it in Bash, which I quite like. So this might not be entry-level friendly, but if you're even an intermediate level, and definitely if you're a senior, regardless of your main language, you're going to be using Bash for build, deploy, file system operations, terminal navigation, and so forth. So it's really cool that you can write this super basic data store, which is using just a text file called database. And you can just do two functions and you get this key value store, which is really great. I love that intro to databases is taking this approach. And then we quickly get into the need for indexes, because if you have a key value store where you set a key and then you go retrieve it in a plain text file, you can see that appending is super fast, but you need to scan through every line to do your grep, and that's super inefficient, right? And so that is a perfect segue into the need for indices. Love that. We're quickly turning to the fact that commercial ones in practice are formed as hash maps. So a great example would be Redis, which is basically a key value store that has an internal hash map. And then we get into some of the complications. They're not going to use plain text because binary is more efficient. Cool. Crash recovery. He talks about deletion here. So we come back and say that we do need deletion after all. Partially written records in the case of a crash, and concurrency control when you have many clients accessing one database. Those are going to all be practically important things. And then writing, so just appending to the log is fast, but in practice, reading is so slow that we're going to make a trade-off. And we're going to keep our writes sorted in many cases when we use a B tree, which is really common, a binary tree organization. So we might have our records written by key in alphabetical order, and that makes lookup much, much faster. And the trade-off is that the write is no longer constant time, now it's log time. So you can see that this is targeted to an intermediate level discussion, and we call this an SS table where the keys are sorted. So it's sorted by key. And we can see that this is an intermediate level discussion. We're already assuming you know about binary search and ologin time and bash. But provided that you know those things, this is a really fantastic chapter. Talks about Lucene, and these are some more specific data stores. So Elasticsearch and Solr. So Lucene is going to use a whole token in the term dictionary. So it's not just using a prefix like a try, it's using maybe a whole word like banana. And one thing that's a gap here, he doesn't get into modern vectorized token search. I would love to see more about that. That is really recent though. In terms of system design tests, we actually don't care about these database internals. We just care if it's SQL or NoSQL. It could be interesting to mention columnar sort, or if you're doing a graph database or something strange. But this is worth calling out because he says ahead of time, Martin says, benchmarks are inconclusive about whether an LSM tree or a B tree is faster. So again, in practice, in your app, you're going to A/B test them. And in practice, in a system design interview, we just don't care. We just talk about SQL or NoSQL. He does talk about fuzzy indexing, fuzzy search, and this starts to go in the direction of document classification and ML. And so he kind of waves his hand at the vector data stores, although we don't really talk about it, but it's good that he kind of, I don't know, creates the road even though he doesn't drive down the road, if that makes sense. I thought this was an interesting note. The performance of in-memory databases is not due to their reads, which I thought it was because of the hash map analogy. You have an O1 lookup. He's saying that it's actually because they get to avoid the encoding for writing to disk, which is an interesting fact. So our intuition from hash maps carry over, coincidentally, it seems. I thought that was interesting. Talking about transactions, he says it doesn't necessarily need to be ASYN compliant. This is not the way the jargon's used, though. He says it merely means low latency read and writes, as opposed to batch. This is not the jargon we mean, though. Typically, when software engineers talk about a database transaction, we're talking about a collection of moves that fail or succeeds together. So I might have a whole SQL query that does a number of things. It might update multiple records or whatever. And those things would fail or succeed in a single transaction. Is typically what we mean. And finally here, I complained about this in chapter 2, but now he's saying data analytics has very different access patterns. That's a big deal, and he doesn't go into this enough, in my opinion. He starts to get into quote-unquote analytical data models, but really what he's talking about is OLAP versus OLTP. OLAP, we might call that an analytical DB. This might be like your Snowflake or your Redshift. OLTP might also be called an application database or a runtime database. This might be your Postgres that is actually connected to your server. And so basically you don't want your data analysts querying the runtime server. You want them to have some disconnected database. And there's a bunch of reasons for that. Performance reasons at runtime, when your analysts need to do queries, we don't want your users impacted, right? But also we don't want to bloat your runtime database and make it super huge so that every deployment you're dealing with this like major database. You want to keep those separate. Your app DB can be smaller and your big old warehouse can be more isolated. So that's interesting from like what tool are you going to use perspective, but he doesn't actually deal with the data model and the fact that there are certain events that developers care about, certain logs that developers care about, that analysts just don't care about. They actually have different data modeling concerns, not just different tool concerns. There is a good call out to what I consider to be a difference between small data and big data, which is like just the existence of a warehouse. Like if you're a small business, you might not have a warehouse at all, and that's totally fine. So what are the indications that you're dealing with big data? One of them is just that you have a data warehouse at all. He talks about star and snowflake schemas and fact tables. I've heard these called transaction tables, but I haven't worked at Walmart, so yeah, I guess he's saying that they would be called fact tables when you go through the checkout and buy 12 6-packs of soda or whatever you're doing. I would just call that a transaction, admittedly in a different sense than a database transaction, but I've also heard that called a transaction table. But I guess maybe fact table is a better term, or a more formal term maybe. Column-oriented storage is actually a big deal. There's a crazy amount of performance, cost, and efficiency difference that you can take advantage of if you only care about a few columns in your queries. Columns can do vectorized processing, where you use like and or bitwise operators. This is not to be confused with vector search or a vectorized database. Vectorized processing literally means we're using bitwise operators. Materialized views are super cool. They're basically caches, so they're going to speed up your reads. And that's about it. Those are some of the things you need to do or need to know about when it comes to database internals and analytical data stores. Join me for chapter 4 up next. We'll talk about encoding and evolution.